So yeah, we have two short courses this morning. The first one is about the science motivation for main infrared mission like life, trying to detect and characterize Earth-like exoplanets. And our first speaker is Dr. Tiffany Kataria from JPL.
All right, thanks, Bertrand. Okay, so kicking off this workshop this week, no pressure, but I just wanted to provide somewhat of a palate cleanser, one might say, in terms of really motivating the fundamentals of why we're even doing this in the first place. And so with that, I'll dive in. So when I usually, the past couple times I've given this flavor of talk, I've started with a picture of the Earth, thinking about all of the complex processes, geochemical, atmospheric, interior, the properties itself, inherent to the atmosphere, the clouds and so on, the weather, thinking about all of these three-dimensional, complicated processes. And really the challenge that we face here is taking all of that into just a pinprick of light. And so this is the classic Voyager 1 image of the pale blue dot. So this was taken as Voyager 1 was exiting the solar system. And so that blue pinprick there you see is Earth. And in fact, our challenge is even more difficult, right? This is within a single solar system. And so imagine, all of those complex processes encapsulated within one tiny pixel in our case. And so this is really, just the challenge that we're facing here in terms of understanding what life might look like on another, Earth 2.0. And so my talk today will kind of focus a bit on understanding Earth life, because really that's our only data point in understanding how life arises on another planet. So, driving home the point that understanding Earth-like helps us to search for life elsewhere, which may be obvious, but I think I'll, outline in many different ways, just kind of framing one's mind into thinking about what that really means when we're looking for life on an exoplanet. So here are these just two images. Here on the left is just an image of microbes, very small microbes. Then this is really the life we're considering, at its smallest level. And then here on the right is just a graphic of, the chemical reaction for photosynthesis, taking carbon dioxide and water to produce glucose and oxygen. Okay, so I'll warn you first before I dive into a lot of these very technical graphics. This is meant to, just paint the picture, and I don't intend to go through any of these figures in any depth, nor am I an expert enough to be able to go into any depth. So, but this is what this workshop is all about. So anyway, just to, again, paint the picture, one thing to consider, of course, is that Earth and its life have actually evolved together. And so one should really consider that in the evolution of life on another planet. So these two graphics are basically illustrating that. I know the text is a bit small, but basically these two figures are showing, the geologic history of Earth from the Hadean through to the Cenozoic era. Here on the right, you're seeing that same timeline go on the x-axis. But plotted against all of the geochemical processes that are taking place are the big tent poles in terms of the evolution of life, in particular this great oxidation event. And so Earth's atmosphere was very anoxic early in its evolution, and then this rise of oxygen led to many different processes taking place, the earliest start of photosynthesis and so on. And so really at the end of the day, the history of life on Earth is also the history of oxygen. And so a question I will pose to you this week is, what might that timeline look like for another world? We're probably not going to answer all of that this week for sure, but again, just to kind of get your mind working here. So one thing I'm interested in most recently, and work that I have funded at JPL, thanks to Charles and others, is understanding the origin of life on exoplanets. And so there's a lot of discussion about, biosignatures, these signatures of life that you might see in a spectrum. But fundamentally, what we're considering is, are these planets, do they have the conditions for life to even arise? And so this is just an overview of so a lot of these slides are from Lori Barge, who's my colleague over at JPL, who I'm working closely on this project with. And so she's really the chemist, the origin of life person on a lot of this, and has been teaching me a lot over the course of these many months and soon to be years. So this is a timeline of the origin of life on Earth. This is somewhat of a misnomer in that the origin of life itself is actually a process, not really an event, so to speak. But just to illustrate here, this is just the geologic timeline. And over here, origin of life essentially is happening kind of rises in the middle of this timeline here, about 4.4 to 4.1 billion years ago. And so one talks a lot about the first evidence of life, backing up from that time to the last universal common ancestor, or LUCA, which you might have heard about. So that's really our most common ancestor to life as it exists today. But you can really take this timeline as a whole and approach the origin of life from kind of two directions. And so one is to take the first evidence of life and look at, the genetic makeup of that and see, how much of these might be related to pre-LUCA genes and pre-LUCA enzymes, and kind of work your way backwards. But the approach that Laurie Barge and other colleagues take is to, start from the formation of Earth, take the abiotic organic chemistry and prebiotic chemistry, prebiotic meaning it's really just a type of abiotic chemistry that's more of the precursor to life. But starting from those early reactions to try and understand, in those early Earth conditions, how life might arise. Ideally, of course, these two approaches should meet in the middle for origin of life, but I'd say that's very much a work in progress. And so there are various, thinking about Earth, various environmental settings that are proposed for the origin of life. So one in particular that Laurie and her colleagues are very interested in is hydrothermal vents. So at the deep ocean, it's actually posited that a lot of the early life was probably chemotrophic, that is, didn't rely on photosynthesis to arise. And so hydrothermal vents seem to be a good candidate for where that life might have arisen. It's very hot. There's a lot of really dynamic chemistry taking place there. It's really also favorable for ocean worlds, which has risen into prominence within the solar system for our understanding of where life might actually currently exist, places like Europa and Enceladus and so on. But of course, there are other environments, very chemically rich environments where Earth's origin of life might have arisen. And in fact, it could have arisen in many different places, but maybe it just failed in others. And, one is the one that persisted and led to LUCA and so on. So really there's, even within our own solar system, there's such a diversity of environments where life could have arisen and maybe failed, and maybe other places persisted. So here are some questions, that really drive astrobiology and origin of life, mainly for ocean worlds, but you could imagine applying a lot of these same questions to exoplanets. So the first three are maybe more general to these ocean worlds, what gradients are present in primitive ocean world vents, what minerals and metal catalysts are present. Those are the sorts of things we can start to ask. What's the geochemistry of the ocean, rocks, and ice that form these environments? But then these more fundamental, I think, deeper questions, how would Earth-like prebiotic reactions be different under different conditions, say around an M-dwarf star? That was something that Laurie and I started thinking about pretty early on. What sort of biotic histories are even possible to begin with? And what would the biosignature threshold be for a particular world? Biosignature threshold being, the detection of a particular thing that might constitute life or non-life. And so, of course, these are pretty Enceladus specific. That's what this graphic is showing here. But again, could be extended to thinking about, exoplanets in general. And so when one investigates biosignatures, you can think fundamentally that this is really a question of how can we differentiate between life and non-life, between biotic and abiotic elements. And so this is a cartoon graphic from a recent review paper that Laurie and her colleagues put out in Astrobiology in 2021, presenting this idea of this biosignature threshold. And so it's really, this limit of complexity or whatever metric above which you would classify some detection as biotic versus abiotic. And so in the case of an in situ mission, say to Mars or whatever, this could be some identification of peptides or lipids or fats or whatever that you could consider to be related to life. So A through E are really showing these from the origin of life literature, things that people have identified as related to life, but could in fact be made abiotically in the lab. But the threshold relates to kind of what context, what environment you're considering to begin with. So say, we find an enzyme on Earth, we're pretty confident that's related to life because we know there's life there. But if we consider Enceladus or Europa, or perhaps an exoplanet where we don't really know the context of the whole environment it's in, if we detect that enzyme, the threshold for then saying this is a biotic environment is much higher. And so we really need to understand the gap between that, the biotic and prebiotic world to understand when we see something if that is related to life. Okay. And so, the real challenge, this is like how I like to frame this, and that's a typo, apologies, approaches to identifying biosignatures, to me, they kind of bifurcate in these two ways, depending on if you're thinking more in the planetary science context versus an astrophysics one. And so if you're considering some local biology, I think these are different colored rocks depending on different microbes that are present in the soil. That's what causes those colors. So in the case of planetary science, right, of course, they have the great benefit of being able to send a rover or an orbiter to their object of interest and be able to make in situ measurements, even remote, orbital measurements. But, there's a lot of spatial context with that, and many ground truthing on various levels. And so with that, I would arguably say, pretty deep understanding of whether or not you're looking at conditions that would be favorable for life. I think Mars, in Mars science, they're detecting water over and over again, which is great. But in astrophysics, of course, we have the challenge of, these remote detections of so-called biosignature gases. So these atmospheric signatures, maybe they're from the surface, but we see some signatures that we might identify, okay, these are relevant for life processes on this particular planet. But these are mostly, global conditions. These are remote measurements. And so tying that back to the actual, microcosm of environments that might be taking place on this world is very challenging. And so this is kind of the framework, I think, that's been adopted in a lot of frameworks for understanding biosignatures. So this is a review paper from Sean Domingo-Goldman and Jason Wright from a number of years ago. So the same classification here they apply, in situ versus remote biosignatures. So in the case of in situ biosignatures, you have all sorts, visual, chemical. I don't think we'll have, well, I don't know. If we find fossils on an exoplanet, I think my mind would be truly blown. But, we don't really have that benefit here. And then, of course, there's a bevy of biological molecules that I think we well understand because, again, we have for these in situ measurements a lot more contextual information. And in the case of, the measurements that can be made, you can throw a gas chromatograph on Mars and actually measure the soils in situ, right? There's a lot of information that you can get from there. Whereas, when it comes to remote biosignatures, I'd say, we're still continuing to flesh out what those look like, right? Ultimately, life is a disequilibrium process, and so identifying any sort of disequilibrium chemistry on a potentially habitable planet might itself be indicative of life, but I think there are lots of studies to look more deeply into that. Ideally, of course, we'd like more spatially resolved measurements, some geochemical structures of intelligent life, one can dream. And then, of course, intelligent broadcasts, institutes like SETI trying to transmit out and then be sensitive to any transmissions that could come in. And so in my mind, this really, this is a nice summary graphic that really, I think, boils down the problem. We're looking at atmospheric measurements, and so we want to understand what life itself produces. But if a dead planet can fool us, we might be detecting a molecule that could be produced abiotically and in fact is, and it's in fact a dead planet. And so, we're reaching the wrong conclusions. With exoplanets, of course, there's also the lack of data, a lot of spatial coverage in many cases, and thinking about more deeply how do we quantify those uncertainties, not only in the measurement of the molecule, but our assessment of life itself. And so there are many different approaches. This is just kind of a high-level overview, again, just a palette or an appetizer, so to speak. And so I think maybe Michael will talk, I don't know if it's this 2013 paper or another one, I believe there are two. But this is, one approach one can take to investigating biosignatures. So this is a paper from Sarah Seeger from a number of years ago, basically linking biosignature gases to biomass estimates from the literature. So basically asking the question, if you consider the biomass that's produced on a place like Earth, is that a plausible amount, or does that biomass actually lead to a detectable spectrum, and is that plausible? Do those go hand in hand? And so I think this is a really interesting line of investigation that's, I think, since borne fruit in many different arenas. Just a quick divergence before I launch into a couple more things, but I just wanted to, underscore the power of the mid-IR for investigating biosignatures. And so these are actually two figures. Oh gosh, they are the blurry versions, I apologize, but hopefully you can read them for the most part. And so these are just two figures from the Origin Space Telescope report, which I encourage you to look at for the high resolution versions. But basically, this is really highlighting the power of the mid-infrared. Both of these are illustrated in wavelength, which again, I apologize, is hard to see. But basically, this left figure here is showing how habitable zone planets emit at the wavelengths that we're probing. The peak of their infrared thermal emission is at the wavelengths that we'd be interested in. And so it's really powerful for understanding the thermal structure of these potentially habitable worlds. The right figure is highlighting the range of absorption features that are present in the mid-infrared. And so you really want, ideally for retrievals, for understanding the global properties of the atmosphere, you want multiple molecular detections. JWST is showing this already. And so here in the mid-infrared, highlighting various important signatures for biology, for life: oxygen, ozone, nitrous oxide, methane, and so on. And I'll just note here, and I'm sure this will come up later maybe in discussions, but Origin's considered basically biosignature pairs. So ozone and methane, and ozone and nitrous oxide, that was our kind of definition of what a biosignature constituted. But since then, these are actually two 2022 studies. So, this area is very rich and moving very fast, I think. So these are just two recent papers. The first here on the left by Eddie Schwieterman, investigating nitrous oxide alone as a biosignature. And so this is just showing thermal emission spectra for an Earth-like planet around different stellar hosts, from a sun, a G-type star, a K-type star, and M-type, and two early and late M-type stars. And so basically this is varying the teramole per year, so the amount, essentially the amount of nitrous oxide in the atmosphere, and seeing, how detectable those features would be, to the precision of some future telescope. And so I'm highlighting this here because all of basically the major conclusion of the paper was that nitrous oxide would be a really interesting biosignature to investigate in the mid-infrared. So I was like, great, check, done. And so in particular, they point out that K-dwarf stars are actually really ideal for this. So you can see this kind of deep nitrous oxide absorption here at these two wavelength ranges. So they point out that this would be interesting to investigate with future models, but of course future telescopes. Correspondingly, this was a paper put out by Long et al. 2022, presenting methyl bromide as a potential biosignature, which again could have some potential features in the mid-infrared. Yeah, and so, I think even in recent years, there's been kind of deeper investigations, not just beyond, not just thinking about the future ERUV telescope or whatever you want to call it. Yeah, great. But thinking more, even more in the future, which I think is great. I'll just skip over this. I have just 2 slides, but I'll just highlight, for the Origins report, we did do a trade study. We can talk about this later. But investigating the ideal wavelength ranges to confidently measure certain gases and so on. But future, projects that I think Ellie Nora will be talking about and so on, should look more deeply as to the performance of, so here on the left is just retrievals for different abundances as a function of wavelength range. Here's just a spectrum showing the different features over 1 to 30 microns. And so, of course, so future studies should really look more deeply into this, considering, more broadly, I think, different stellar types and planet types. And so this is my last slide. Again, this is just, giving some food for thought here. But, in my mind, the search for life requires complex trades to investigate, the ideal architecture for a telescope, but also, considering a more holistic treatment of exoplanets and their environments. This is a summary figure from Meadows and Barnes. It's used quite frequently, I think, just illustrating, how difficult investigations like these are, and how the different colors correspond to how well we understand certain parameters. But it really requires a lot of interdisciplinary knowledge, a lot of, deep modeling, future observations, technological development. It's a big problem here we're tackling, but I hope we get to scratch the surface a little bit this week. So with that, thanks.